In this video, we're going to take a look at a few more difficult equilibrium problems involving some heterogeneous equilibria, as well as some KPs versus KCs. We'll also look at some problems with ice tables that involve algebra as well. We need to set up and solve algebraic equations. We'll start with just a simple review. This question is one that is not very difficult. We're given some information about initial conditions. At 25 degrees, some oxygen, N2O, are placed in a 2-liter vessel. And I notice that we're told moles and we see a volume, so immediately I'm thinking about molarities there. And we've got this rather nasty-looking equilibrium, nasty in the ratios 2 to 3 to 4. At equilibrium, the NO2 concentration is found to be this, 0.02 molarity. What's the value for Kc? Pause the video and see if you can set that up and solve. So the first thing I'll notice again is that this information in the first sentence is going to need to be converted to concentrations. We have moles and we have a volume, so C equals N over V for finding concentration. Those were placed into the vessel, so those are the initial conditions. And then down here we see this important phrase, at equilibrium, the NO2 concentration was this. So this is an equilibrium concentration. Because we have initial and equilibrium information, we're going to want to set up an ice table to organize that. So 2 N2Os plus 3 oxygens creates 4 NO2s, and everything is gas phase, so I'm just going to be lazy and leave out the phases. An ice table tells us the initial, the change, and the equilibrium conditions, ICE. The initial concentrations, if we grab a calculator and divide 0.056, we're doing this little C equals N over V. So 0.056 divided by 2 liters. The initial oxygen concentration is 0.0280 molarity. The N2O initial concentration will be 0.0220 molarity. And it sounds from that first sentence that there was no NO2 initially placed in the container. At equilibrium, the NO2 concentration is 0.020 molarity. Now notice that is a molarity, so you don't need to switch it to molarity, so we'll just put 0.020 molarity. Now we can fill the ice table in because we know the entire starting line, and we know one other thing. We know in this case the NO2. If you know everything initially plus one other thing in the table, then the entire table can be filled out. For example, here we can see we started with no NO2 and we finished with 0.02 at equilibrium, so it must have increased by 0.020 molarity. Since the NO2 is increasing, I can tell right away that this reaction is going in the forward direction. We're making some of the products, and that means these two things have to decrease because they're both reactants in the forward reaction. The ratios are very important, so the change line we can now fill in because we know one number now on the change line, and we see the ratios 2 to 4, so 2 N2Os for 4 NO2s, so it's going to lose half as much as the NO2 gained. So the NO2 gained 0.02, this will lose 0.010 molarity. The oxygen's a little bit harder. You can say 3 to 4. You could argue that it's going to be 3/4 or 75% of 0.02. Alternatively, we could look at 3 to 2 and argue it's going to be 1.5, 3/2 of 0.01. Either way, you should get the same answer. This is going to lose 0.015 molarity. So again, that's 3/4 of 0.02. Or it's 3/2, 1.5 times 0.01, the change for the N2O. So now we can grab a calculator and we can evaluate how much is left at equilibrium. For the N2O, we had 0.022 minus 0.01, so we have 0.012 molarity. And for the oxygen, we have 0.028, and we take away 0.015, and we get 0.013 molarity left there. And when you add or subtract numbers like this, you round off the answers according to the number of decimal places. Since this had 3 decimals, we're going to round off to 3 decimals in these 2 answers. So now we've got the concentrations at equilibrium, we can go find Kc. Be sure you're always writing the Kc expression, concentration of NO2 in this case, the product to the 4th, over concentration of N2O squared times oxygen concentration cubed equals 0.020 to the 4th over 0.012 squared and 0.013 cubed. So the Kc will equal, be sure you always double check your arithmetic, that you place things in the right places, etc. Those are easy ways to make a simple little mistake and get the answer wrong. So 0.02 to the power of 4, and then we divide, clear that again, 0.02 to the power of 4, this is a new calculator, so I'm still learning how to use it, divide by 0.012 squared, and divide also by 0.013 to the power of 3, equals, Kc is 506. Now technically I should keep 2 significant digits in the Kc value, so technically 5.1 times 10 to the power of 2 is what I should say, but 506 has 1 extra digit, that's probably sufficient. Alright, let's jump in and look at another question. This one I can see right away involves a heterogeneous equilibrium because there's solids and gases present, and that's important because solids are not included in the equilibrium expression. A student placed 10 grams of solid magnesium carbonate into a 5-liter container, heated the system up to 110 degrees. The magnesium carbonate decomposed slightly. At equilibrium, there was this much, 8.15 grams of the magnesium carbonate left. What's the value of Kc for this reaction at this temperature? Now we have a small problem here. You might be thinking to yourself, well, I'll convert the grams to moles, which is good, and then the moles to molarity because there's a volume, but right there you fall into a bit of a trap. The magnesium carbonate is a solid substance. So if you imagine this 5-liter flask, here's our 5-liter flask, the magnesium carbonate does not fill the flask. It's just sitting here on the bottom, the 10 grams. The 5 liters is going to be the volume for the gas, for the CO2, but it's not the volume for the solids. So it doesn't make any sense to try to go find a molarity using that volume if we're going to talk about the solids. Because of that, because there's solids in here, and the only information given, 10 grams and 8.15 grams, refers to the solid, then what I'm going to do is do a little something different. I'm going to do my ice table, but instead of doing it in molarity or pressures like we normally do, I'm going to do it in moles. So in this question, I'm going to use moles, which is fine because the balanced equation is in terms of moles as well. So I can use moles in the table. So if I take the 10 grams of magnesium carbonate and just convert it to moles, get rid of grams, put in moles using the molar mass, or if you want to use your little formula, moles is mass divided by molar mass, that will also be working here. So magnesium carbonate's molar mass, 24.31, the molar mass of magnesium, 12.01 for carbon, and 3 times 16, the oxygens, 84.32 grams per mole. So 10 grams divided by 84.32 is 0.119, or I guess 0.1186 would be the correct number of sig figs, moles of magnesium carbonate initially. Okay, that's what was placed in the container. They had 8.15 grams of magnesium carbonate at equilibrium. So if we do the same thing, switch to moles, we get 8.15 divided by 84.32, we get 0.09 3 sig fig, so 6.7 moles of magnesium carbonate at equilibrium. So now I'm going to fill in this ice table using moles, and then we'll focus on the gas because it's the only thing that's going to be in the equilibrium expression. So taking the initial moles of magnesium carbonate, 0.1186 moles, and at equilibrium, 0.0967 moles. Now, from the way the question read, the only thing placed initially in the container was the magnesium carbonate, so the MgO and the CO2 both start at 0. That's important because it means we actually do know what their amounts were. Now we can do what we've done in the past. We can figure out that the MgCO3 must have lost something since it began with 0.1186 and finished with 0.0967. We can see how much it lost. So 0.1186 minus 0.0967, it lost 0.0219 moles. And then the ratio 1 to 1 to 1 means that these guys on the other side of the equation gained the same amounts, 0.0219, 0.0219. The ratios apply to pressures, they apply to molarities, they apply to moles as well. They do not apply to grams. We could not put grams in here and then use the ratio because the molar masses are different for the different substances. So we've got 0.0219 moles of each of these at equilibrium. The initial amounts were 0 and we gained that amount. Now, the only thing in the table which is going to be part of my equilibrium expression is CO2. So if we now write the CO2, the Kc expression, Kc is equal to, the product here is concentration of CO2, and it's the only thing that's going to be in the expression, over 1 if you'd like, because there are no reactants here to be included because they're all solids. Remember that solids and liquids have constant concentrations. They're not compressible, and so their concentrations are constant. That means that we don't include them. We only include gases and aqueous species because their concentrations can change during a reaction. Since there were no reactants to include, we'll just put over 1, or in this case we really could have just said concentration of CO2, because to divide by 1 doesn't do anything. If we're looking at the reverse reaction, though, then we would have to say Kc for the reverse is 1 over concentration of CO2. There, it's important to put the 1 in because it's in the numerator and is therefore needed to make a logical fraction. So in this case, all we need to know is what was the concentration of CO2. So if we grab our little formula, C equals N over V, we can say the moles was 0.0219 moles, and the volume was 5 liters. So equals 0.0219 divided by 5 liters, and we get 0.00438 as the value for Kc. So that question was a little bit tricky because it involved solids and gases, so it was heterogeneous. Now, normally, when we see solids in an ice table, I would normally just put an X underneath them and say we're going to ignore them in the ice table. The problem here, the reason we couldn't ignore them, is because the only information given in the question about the starting and equilibrium amounts referred to the solid. So we were not allowed to simply ignore them in this question. All right, here is a third problem. Again, you can pause the video here and try this yourself if you'd like. A chemist is studying the reaction below for which Kc is 0.085 at a given temperature. And we see here a reaction with two NO2s decomposing into NO and NO3, and we notice that everything is in the gas phase. Everything here is homogeneous gas. We've got 5 moles of NO2 in a 10-liter vessel, and that was placed into it, so that's the initial conditions. What mass of NO would be in the container at equilibrium? So there's an initial set of conditions, and we're asked about equilibrium, so that's a clue to set up an ice table. So 2 NO2s, and again, because everything's homogeneous, I'm just going to leave out the phases, plus NO3, there we go. And ICE, the initial change in the equilibrium. The C equals N over V is going to be helpful here. 5 moles in a 10-liter vessel, 5 divided by 10 means the initial NO2 concentration is 0.50 molarity. It was the only thing placed in the vessel, so the NO and the NO3 start off at 0. And now I run into a bit of a problem, don't I? Because in this question, we're not trying to find Kc. In fact, we were given the Kc at the top of the question. It was 0.085. So this is a little bit of a different problem. Instead, we want to know how much, and the fact that it's asking for mass is a little bit of an annoyance, but not a major one. What mass of NO, so we're looking for the amount of NO at equilibrium. Well, there's nothing else to put in this table. There's no other numbers to put in. So therefore, there's no way to fill out the table using numbers. So what I'm going to do now is use algebra. I'm going to use x's in this table. I notice that the two products started with nothing, so right away I can tell that they have to increase in concentration, and that would mean the NO2 has to decrease. Looking at the coefficient for NO2, its coefficient is a 2. So if I think about the ratio, what I'm going to do is let it lose 2x. By saying it loses 2x, I can now look at the ratio 2 to 1, the NO's coefficient is a 1, and conclude that it would gain half as much. So instead of gaining 2x, it only gains 1x. And likewise, the NO3 is also a 1 to 2 ratio, or I could look here and say it's 1 to 1 with NO. Either way, I get the same result. It's going to gain x as well. And so now at equilibrium, you'd have 0.5, the starting amount, take away 2x. You'd have 0 plus x is x, and 0 plus x is x. There's my ice table filled in with algebra. Okay, and a clue again, you might want to make a note in your margin. You fill in the table with algebra, with x's, when you know the starting conditions, but nothing else in the table. We'll see an example of a slightly harder problem in just a few minutes where you fill it in with x's for a different reason. So now I'm going to set up the Kc expression, because if we've got algebra, we need an equation. And the Kc here is the equation we're going to use, so NO concentration times NO3 concentration over NO2 concentration squared. So now the Kc value was 0.085, that's where I'm going to use the Kc that was given in the question, and say that that equals, let's substitute these three things into this expression. So substituting x and x into the numerator, we get x times x, which is x squared, over 0.5, I'm going to put that in brackets, 0.5 take away 2x, because it has to be squared as well. Its coefficient is a 2 in the equation, so squared. So now our job is to solve this equation. If we can solve that equation, well, then we found x, and once we know x, we know the concentration of NO at equilibrium. We can then go find the mass at equilibrium. So how do we find x? Well, there's a couple of ways to do this. There's at least 3 or 4 different ways. One way in this particular question that works is because I notice that the numerator is squared, as is the denominator. Because they're both being squared, what I can do to simplify is square root both sides of the equation. If I square root both sides, the square root of 0.085 is, let me find my square root button on this new calculator, so the square root of 0.085 is 0.2 0.29 will equal x over 0.5 minus 2x. So square rooting here made sense because there was something squared over something squared. Please, please, please do not make the silly algebra mistake of thinking that you can simply cancel those squares. You cannot cancel them, but you can get rid of them by square rooting. Now, if one of them was being squared, say the top, but not the bottom, then square rooting would not help here. You can only be helpful by square rooting if you have squared on top and on the bottom. So now by square rooting, we've changed our equation from essentially a quadratic equation that we had up there into a linear equation. So 0.29 multiplied by the denominator will equal the numerator. And now multiplying through the brackets, 0.29 times 0.5 is 0.145. Take away 0.29 times 2, 0.58 x's equals 1x. And now I'll add 0.58x to both sides. 0.145 equals 1.58 x's. And now I'll divide by 1.58. X will equal 0.145 divided by 1.58, which is 0.092 molarity. Okay, so there is and notice looking at my ICE table up above, what did X represent? It represented several things, but one thing it definitely represents is the concentration of NO at equilibrium. So I can go back down here and say this is equal to the concentration of NO at equilibrium, EQ. Now let me just quickly finish the problem. Since we know the concentration at equilibrium, we wanted to know the mass. So we can use formulas again, our two little formulas that we use all the time, C equals N over V, moles equals mass over molar mass. If we use those two formulas in that order, we can find the mass. Alternatively, we could use a couple of unit multipliers. We can take the volume, 10.0 liters, and we can get rid of liters and switch to moles of NO, and then get rid of the moles and switch to grams of NO. And you can see we're doing the same basic thing, but with unit multipliers. The moles per liter is my concentration, so 0.092 moles for every liter, and then grams and moles is the molar mass. 1 mole weighs 14.01 plus 16 is going to be 30.01 grams. So 10 times 0.092 times 30.01 is 27.6, or I guess with two significant digits, 28 grams of NO at equilibrium. All right? So, was there another way to solve this equation rather than square rooting, or what if you weren't able to square root to solve it? Well, it is a quadratic equation, so if you feel really brave, and I really don't recommend this because it gets ugly, is you could have expanded 0.5 minus 2x squared. Now, if you'd be tempted to think that that means just squaring both of them, then don't do this method, because that's not correct. When you square a binomial, you get a trinomial, don't you? So when you take a minus b and square it, you get a squared minus 2 times a times b plus b squared. So when we square this binomial, we'd get 0.5 squared minus 2 times 0.5 times 2x, and then we'd also get a 2x squared at the end. It's ugly, it's messy, and then you'd have to rearrange, you'd get a quadratic equation with completing the square and things like that. I really don't recommend that technique. If you own a graphing calculator, there's a couple of other approaches you could use, and let me just quickly illustrate them here. I could, if I felt brave, is I could graph this. This is actually not that hard. what I'm going to do is think of this 0.085 as y1. It's going to be one graph on my calculator. And this on the right, this ugly quadratic stuff, is going to be y2 on my calculator. And what I want to do is say, where do they equal each other? So on my calculator, I'll go y equals, I'll type 0.085 as one graph, I'll type x, this button here, xt theta n is your x button, so x squared divide by bracket 0.5 take away 2x close bracket squared. That's my other equation. Now what I'll do is I'll just graph that, zoom standard. Now this is probably not going to look very good, so let's think about the range for a moment. I'm going to go to the window settings, and I noticed, I'm thinking about the chemistry, x's can't be negative in my chemistry, so I don't have to start at x of negative 10, I'll just start at 0. 0.5 minus 2x puts a limit on how big x could be. 2x can't be bigger than 0.5, or I'll get a negative concentration at equilibrium, which means that x can't be bigger than 0.25. So my maximum x is 0.25. The scale, if I'm going to go from 0 to 0.25, or maybe I'll just go up by 0.05s. That's just the scale on the graph. The y values, I just want to see what this equation y equals 0.085 looks like, and you know that y equals a number should give me a horizontal line. So to let me see 0.085, I'll just let my minimum be 0.08, and I'll let my maximum be 0.09. So 0.085 is going to go right through the middle there, and my scale would be maybe 0.001. So it'll be 10 little tick marks in between. I think that makes sense. If I graph now, there's the horizontal line, which is y equals 0.085, and now the graph should also show me this, and just a piece of it, and here it is here. This vertical line is where the right-hand graph equals the horizontal line. So what I'm going to do now is second function calc, right above the trace button, and I want to calculate the point of intersection, number 5. So I'll move it says, are you on the first curve? I'll just press the yes button, yes I am. Are you on the second curve? And it shows me at the top the equation, yes I am. I'll press enter, and so give me a guess. Well, what I'm going to do is move my cursor over until I can see the dot there. Now I'm at x equals 0.17, and I don't see my cursor. Now the y values are getting bigger, so I must have gone past. So I'm going to go back the other way, remembering that I'm only looking at about 0.085, so looking at those y values, I should be getting close. They're coming down, they're coming down, they're coming down. The y values are getting smaller. Where is that cursor? There it is. So now that I can see the cursor, here's this dotted point right here, I'm going to estimate an x value. Now alternatively, I could have said to myself, well, I know because I set the window settings that this is going from 0 to 0.25, so this would be just under half. I could say, well, it's about 0.1 or something like that. So I'm going to use a guess of 0.1. How's that? And now I'll just press enter, and there it tells me the point of intersection. It tells me that x equals 0.092. And if you compare that to what we got down below with algebra, it's the same answer that we had earlier, 0.092. All right? Now what would you do here? You would simply tell me from the TI-84, TI-83, from your graphing calculator is really all you need to tell me. Is that little statement from my TI-84 replaces the need to do all this algebra. Okay? Now that's the sort of applied math graphing approach to solving this problem. There is another way to do it using your graphing calculator, and that's to use the solver feature. You've probably never seen this before, so let's work on it. Let's do it real quick together. You have a button that says math on the calculator, so let's press the math button. And if you scroll down the math options, you'll see that there is an option. Mine says option 0, which is the solver. So I'm going to press that. Now I've used the solver in the past, so on my screen of the calculator there's an old equation that I've solved, and coincidentally it looks to be the same answer as the one we just had. Purely by coincidence, I guarantee you. I'm going to press the up arrow to get back to the equation, and I'm going to clear the equation. If you've never used the solver before on your calculator, then this is probably what you see. So you'll notice that the solver wants me to enter an equation, but in the form 0 equals. But the equation we're solving says 0.085 equals. To get it to say 0 equals, I'll just move the 0.085 to the other side of my equation, where it'll become minus 0.085. So now I'll have 0 equals, so let's type in the equation, x squared divide by bracket 0.5 take away 2x close bracket squared, and don't forget minus 0.085, and then press enter. Now, one weird thing about the solver is that you have to again give it a guess. You have to give an estimate of what you think the answer would be. Well, how do we do that? Well, the good news is that in chemistry, most of our answers by far are going to be small positive numbers. So a guess that will work almost all the time is to simply guess that x is pretty close to 0. Just x equals 0 in that middle line. Don't ever go down and change the boundaries. That's just going to tell us that our answer is going to be somewhere between negative 1 times 10 to the 99 and positive 1 times 10 to the 99. Don't go and change that. So now how do we get it to solve the equation? Well, right above the enter button it says the word solve, and mine's in green. So I'm going to press the green alpha button, alpha, and then solve. And there we go. X is 0.092. And so we get the same answer. And again, you would just say from the TI-84. So that's using the solver feature of the graphing calculator rather than the graphing part of it. So now that I've got the answer, 0.092, from the TI-84, I would go back and now finish it off by saying what we did at the bottom, 10 liters convert to grams. All right? So when you're doing this problem, I would expect to see on a test the equation, the ICE table filled in, the expression, the algebra plugged in here, and then either the algebra solved like we did over here, or this statement here that from my TI-84, x equals this. Okay? All right. Another question, consider this reaction. Bromine, chlorine makes BrCl. We got the Kp. A reaction mixture initially contains bromine and chlorine at these pressures. And I see a little typo there. That's supposed to say torr. Then the pressures are given in torr, and we know that when you're dealing with KPs, you have to use pressures in atmospheres. So we're going to switch those to atmospheres. It turns out that in this particular question, because of the ratio 1 to 1 to 2, the Kp here is going to actually be unitless, and so it is possible in this particular question to solve it using torr, but just out of habit we're going to switch to atmospheres, because in most questions you can't leave it in torr, you do have to switch to atmospheres. So what's the equilibrium partial pressure of BrCl? So let's take those two pressures and switch them to atmospheres. So pressure of Br2 will be 755 torr. Get rid of torr, put in atmospheres. 1 atmosphere, 760 torr, so the answer is going to be very close to 1. So 755 divided by 760, 0.993 atmospheres. And the pressure of the Cl2 is going to be 735 torr. Get rid of torr, switch to atmospheres, and slightly smaller pressure. So 735 divided by 760, 0.967 atmospheres. Now those were the initial pressures, so these are the initial, and we are looking for the equilibrium pressure of BrCl. So again, knowing initial and wanting equilibrium, that's a signal to set up the ICE table. So bromine plus chlorine makes BrCl, and these are all gases, so I'll be lazy again and leave out my phases. We usually use molarities in the ice table because we're usually dealing with a Kc. This question is a Kp, and so instead we're going to use atmospheres. So the initial bromine pressure was 0.993, the initial chlorine 0.967, and there was no BRCl in the container. Now notice we do know the Kp value. When I know an equilibrium constant like this, and I know the initial conditions, or as we said in the last question, when there's nothing else you can really put in that table, there's nothing else in the question that would make sense to go in the table, then those are signals to use algebra. Since the BRCl starts with nothing, it has to increase. You can't decrease if you start with 0. And so this reaction, like before, is going forwards, so minus minus plus. Things on one side are increasing, things on the other side of the equation are decreasing. The coefficients are 1 to 1 to 2, so we'll say this guy loses x, 1x. This will lose the same amount, 1 to 1 ratio, and then this will gain twice as much, 2x. So at equilibrium we have 0.993 take away x, we have 0.967 take away x, and we have 2x. Now those are pressures. So if we set up our Kp expression, pressure of BRCl squared over pressure of bromine times pressure of chlorine, and now let's substitute the Kp value was given up above as 1.11 times 10 to the minus 4, and that's got to equal 2x, careful here, squared, so put it in brackets, it's not the same as just 2x squared, divided by 0.993 take away x times 0.967 take away x. And now we have this rather ugly quadratic equation again to solve. Notice in this question only the numerator is being squared, so our option to go and square root both sides of the equation is not here. We cannot simplify by square rooting, but we can still use the graphing calculator, so I'm going to use the solver on my TI-84. So x will equal, and let's type that in. So I've got my graphing calculator, I'll press the math button, I'll scroll down or just press option 0 for solver. Yours might have a different shortcut, so do whatever's on your calculator. I'll go to up arrow on the keypad and clear my previous equation. So now I'm ready to type in the equation, but it wants it to be entered 0 equals. So again, we're going to take the k value, in this case Kp, and we're going to move it to the other side of our equation where it will become minus that value, and now we'll just have 0 on the left. So let's type this stuff in on the right. Now, do not just type 2x squared, because that's not the same as 2x squared. If you want to type 4x squared, because 2x times 2x is 4x squared, that'll work, or brackets 2x, close bracket, squared. That'll also work. Divide by bracket 0.993 minus x, close that first bracket, and divide again by the other bracket, 0.967, take away x. And a very common mistake is to forget that we have to also subtract the Kp value. So take away 1.11 times 10 to the power of minus 4. Glance at the equation, be sure that your brackets are correct, be sure that you haven't mistyped something. Press enter, and the guess that we're going to use on this middle line, we always give it a guess. The guess that will almost always work is 0. Our answers are going to be small positive numbers. And now we want to press the alpha button, and right above the enter it says solve, so alpha solve, and our answer here is 0.0051. So from the graphing calculator, x is 0.00513, I guess. Atmospheres. Atmospheres because that's what our ice table was filled in with, pressures in atmospheres. Now the question said, what was the equilibrium partial pressure of the BRCl? When we look at the ice table, we find BRCL, and we notice that at equilibrium its partial pressure was not just x, it was 2x. So now we can say at equilibrium, therefore at equilibrium, the pressure of BRCL is 2x, which is 2 times 0.00513. So multiply that by 2, and we get 0.0103 atmospheres. Okay, the pressure of BRCL at equilibrium. All right. Here's another problem. Pause the video and see if you can solve this yourself. At 100 degrees Celsius, the Kc value is 4.72 for this reaction of NO2 becoming N2O4. An empty 10-liter vessel is filled with 4.6 grams of NO2. What's the total pressure in the flask at equilibrium? A couple things here jump out at me as annoying. One is the mass of NO2 instead of moles. Minor annoyance, but an annoyance. And the second thing is that the question is dealing with a Kc, but then it's wanting to know about the total pressure. So there's a couple ways to go about this. We could use the Kc and an ice table with concentrations, because it's a Kc, and find out the concentrations of everything at equilibrium, then use the ideal gas law to find the pressures at equilibrium, and finally Dalton's law will give me the total pressure at equilibrium. So we, in other words, use Kc and concentrations in the ice table, then convert to pressures. Alternatively, we could take the Kc value and convert it to a Kp value. We have an equation to do that, and then we could fill in the ice table with pressures and deal only with pressures, since that's what we're looking for. I think that's the method that I'm going to use. I'm going to take my Kc value and convert it to a Kp value. So my formula said that Kp was equal to Kc times RT to the power of change in moles of gas. So in this case, the Kp will equal 4.72 times 0.0821. We always use that value in this formula because Kp's are calculated with atmospheres for pressure, times 100 degrees Celsius will be 373 Kelvin, and then the change in moles of gas, there's 1 mole of product gas, and there were 2 moles of reactant gas. So the change in moles is 1 minus 2, the final minus the initial. So grabbing a calculator, 4.72 times bracket 0.0821 times 373, close bracket, and then raised to the power of -1 equals 0.154 is the Kp value. Now, we've got this annoying initial 4.6 grams of NO2 in the 10-liter vessel at 100 degrees Celsius. So let's go find the initial pressure, since we're going to use pressures, of NO2. The ideal gas law says that pressure is equal to nRT divided by V, if we rearrange it. And we remember that moles is mass over molar mass, so mRT over molar mass times volume. Mass over molar mass is the same as moles. So now we can just substitute 4.60 grams, 0.0821 because we want atmospheres again. Our temperature was 100 degrees, so 373 Kelvin. And our volume, our molar mass, and this is NO2 we're talking about, so 2 times 16 is 32, plus 1401 will be 3246.01. That's the molar mass, and the volume was 10 liters. So the pressure in atmospheres initially is 4.6 times 0.0821 times 373, divide by 46.01, and divide by 10. So 0.306 atmospheres. Now, again, we know the initial situation, and we want the equilibrium total pressure. Don't let that bother you yet about the total pressure. We'll deal with that at the end, but hopefully you recognize we need an ice table. So 2 NO2s becomes N2O4, and again I'm leaving out the phases just because everything here was gas. ICE, initial change equilibrium. The initial pressure of NO2 we just found was 0.306 atmospheres, and there was no N2O4 in the vessel. We don't know anything else at equilibrium, so now that's a signal to use algebra. Fill in the table with algebra. The N2O4 is starting with 0, so it has to increase, and then this has to decrease. Again, that's not always going to be the case that the right increases and the left decreases. Sometimes it's reversed. The substance that starts at 0 cannot decrease, so it has to increase. The coefficient of NO2 is a 2, so we'll say it loses 2x. The N2O4's coefficient is a 1, so the 2 to 1 ratio means it gains just x. At equilibrium, 0 plus x is x, and 0.306 minus 2x is the pressure of NO2 at equilibrium. So now we can set up our Kp expression. Kp is the pressure of N2O4 divided by the pressure of NO2 squared, and that's going to give me x divided by 0.306 minus 2x squared, and that's equal to, we know the Kp value, we just calculated up above, 0.154. So here's an equation, and again it's an ugly quadratic equation where this time the denominator is being squared, so there's no way to square root this to simplify since the numerator is not being squared. So I'm going to use the solver again on my graphing calculator. I'll type the math button and then scroll down to the solver. I'll press the up arrow to get into the equation and clear my previous equation. So I want to type in x divide by bracket 0.306 take away 2x close bracket squared. Now remember the solver has to be 0 equals, so I'm going to take the 0.154 and just bring it to the other side and type minus 0.154. Of course you could have done it the other way around. You could have typed 0.154 minus all this algebra. That would be just as good. So minus 0.154, since I'm bringing the 0.154 to the left in this case. And now enter. The middle line now, I'm going to give it a guess. My guess is almost always just a 0. And now to get it to solve the equation, I press the alpha button, and then right above the enter it says solve, so alpha solve. Alpha solve. X is 0.0122. 122 atmospheres, and this is from my TI-84 solver. Alright, since we know that x is 0.0122, we can look back at our ice table now, and we can argue that the pressure of NO2 is 0.306 take away 2x, so 0.306 take away 2 times 0.0122, and I get 0.282 atmospheres. The pressure of the N2O4 is just x, right? From the ice table, it's x. So that means it's 0.122 atmospheres. And now the question wanted to know, what is the total pressure in the flask at equilibrium? So now we're just going to use Dalton's law, which says the total pressure is the sum of the partial pressures. The pressure of the NO2 plus the pressure of the N2O4. So it's going to equal 0.282 plus 0.0122. So P total is 0.282 plus 0.0122, 0.294 atmospheres. All right, so that was a rather involved question, and it used a little bit of grade 11 chemistry, both in Dalton's law here at the end. The total pressure is the sum of the partial pressures. It also used the ideal gas law earlier. We converted the Kc value that was given to a Kp value so that we could use our ice table in atmospheres. And then we had to use the graphing calculator to solve a nasty equation with a solver. And so it was a pretty involved question. The other way to approach it, again, just in case you did it the other method, would have been to use the Kc value. Then we would have taken the mass of NO2 and converted it to moles, used the volume to find the initial concentration of NO2, and now coming back to our ice table, we would have used concentrations in here and found the concentrations at equilibrium. Then we would have taken those concentrations. We would have done this with algebra. We'd have to set up an equation like this and solve it with the Kc value and the graphing calculator solver. We'd now know the concentrations at equilibrium. Those would have to be converted to pressures using the ideal gas law and then Dalton's law to get the total pressure. So it's really the same amount of work ultimately, just done in a slightly different order. I've got one more question here. I know this is a long 1-hour video, but hopefully you are not just sitting and watching the whole thing from end to end. You're skipping through it as needed. This last question is also a heterogeneous equilibrium. I see a solid and I see gases as products. It says the decomposition of solid ammonium carbamate to gaseous ammonia and CO2 is endothermic. When solid ammonium carbamate is introduced into an evacuated flask at 25 degrees, the total pressure of gas at equilibrium is 0.116 atmospheres. What's the value for Kp at that temperature? Pause the video and see if you can do that yourself. Okay, so the solid was introduced into the vessel. Now earlier we did a question where there was a solid and we were told how much solid was put in and how much is left at equilibrium. In this question, we're not actually told how much is put in. Because of that, I'm not actually going to worry about this solid in my ice table. Let me just write my equation. I am going to worry about the gases, though, because gases are included in the equilibrium expression. Because this is solid, and because we aren't really given any actual initial and final amounts, I'm just going to put a big X underneath that thing, basically saying I'm going to ignore it in my ice table. Now, one note here that's conceptually important, and the question is a little vague, really does need to say this. It's not only important to say that the solid was introduced into the vessel, it's also important to say that there was some leftover solid when the system reached an equilibrium state. If we didn't know for sure that there was leftover solid, we wouldn't really know that the system had reached equilibrium. So there has to be some leftover solid in there to be at an equilibrium situation. So now, we know there was no ammonia and there was no CO2 put in the flask initially. So we can say then that we know the initial situation, 0, 0. But we don't know anything else. We do know the total pressure. We'll use that at the end. Let's say that this increased, and this increased since I started at 0. But again, we don't know by how much. So like before, let's say we'll use algebra. This gained 2x and this gained x. So at equilibrium, we have 2x, and we have x for the CO2. Now, do you see that we have a small problem here? We would be tempted, if you're not really thinking about it, to try to take these and put them into the Kp expression, and like we did before, like we're going to go use the solver. The problem, though, is that we don't know Kp. In fact, that's what we're trying to find. So we can't really do this in the approach that we used just a few minutes ago with the solver. Instead, we got to now use this information here, and we're going to use Dalton's law at this point. The total pressure was given. So P total is the pressure of ammonia plus the pressure of CO2. Those are the only gases in the container. So 0.116, and this is at equilibrium. Right, the question said at equilibrium, that was the pressure, has to equal my 2x plus my x. So these are pressures again, right? Not concentrations. Those are pressures. So it equals 3x. So it's easy now to find what x is. X is going to be 0.116 divided by 3, 0.0387 atmospheres. And looking at my ice table now, x was the pressure of CO2, so equals the pressure of CO2 at equilibrium. 2x is 2 times this, so times 2, 0.0773 atmospheres. And again, looking at the ice table, 2x is the pressure of ammonia at equilibrium. And if we add those together, we'll get 0.116, which was the total pressure. Now we want to go find Kp. Well, Kp can be calculated because we now know the pressures of everything at equilibrium. The Kp expression would be the pressure of ammonia squared times the pressure of CO2. We don't need to worry about the ammonium carbamate because it's a solid. It doesn't actually show up in the equilibrium expression, so there is no denominator in this question. So equals the pressure of ammonia, 0.0773 squared times the pressure of CO2. So Kp will equal 0.0773 times 0.0387, 0387, be sure you check what you're typing, and my Kp is 0.00299. There's the Kp value at 25 degrees Celsius, which was the temperature in the question. And the Kp, again, whenever you quote an equilibrium constant, you need to refer it to the equation, right? That's the Kp for this equation as balanced like we did here. All right, so there's 6 reasonably more challenging equilibrium problems than ones that we've done so far. Hopefully that will help you as you approach your more advanced web assignments.